Sometimes when there is no audience, you feel conscious talking. So I'll share, I'll record, normally record. With all these things, probably start. Yeah. With this slide. Okay. So where we were was, we started looking at. Doing model checking, looking at symbolic model checking, model checking as manipulation of formulas. And as a first instance of the analysis, we are looking at symbolic model checking for checking invariant properties. Okay, and we noticed that this could be done using what is traditionally called just reachability analysis, which consists of just accumulating all the reachable states that are reachable from any one of the initial states in 0 or more steps. And we saw that this could be defined as computing the transitive closure of the transition relation over the initial states, the smallest transitive closure that includes the state, and which could be done by repeatedly accumulating the images starting from initial state. Now, what I observed was that it was useful also to view this as this reachable state, the set of reachable states and its computation, as characterizing it as a fixed point of a function that is defined over, that maps predicates to predicates, that is set of states to set of states, and characterizing the set of reachable states, set of all reachable states, as a fixed point of an appropriately defined such function. For example, here the reachable set is the least fixed point, the smallest fixed point of a predicate mapping function called predicate transformer, which takes, given an arbitrary set, it takes the image of X under T. That's what this thing is, image of T. Image of this some set of states under T, to which it adds the initial set of states. And I noted that the image of X can be computed as an existential quantification over the states that satisfy X, and also map S to some successor state S prime. Okay, and this one is normally denoted as this fixed point is formally denoted as because it's something that is a property of the function tau. It is of tau z. Now, when defined this way, so one can raise the question: okay, what is the guarantee that there'll be fixed points of any such function? That's where the Kleene-Tarski theorem comes in handy, which guarantees that tau, as long as the predicate transformer, which maps set of states to set of states, is monotonic. any monotonic predicate for finite state transition systems, then the least fixed point is guaranteed to exist, and that it'll be unique. We'll get to this theorem later on. First, I want to cover the intuitive notion of how to characterize all CTL operators as fixed points of a properly defined tau, so that you can start implementing them using these. And what Kleene-Tarski theorem also states is when tau is monotonic, then the least fixed point can be computed as the limit of a chain of tau application starting from false. You start from false, you apply tau repeatedly to false, and the result of applying tau to false until you reach it's kind of the union. It's a limit. It's a union of all these taus, which is what is happening here in the picture, until you can't add things anymore. So Kleene-Tarski theorem, it states that as long as monotonic, it exists. There is an infinite version of this thing as well. Finite version is the way that I've stated here. Finite version, if tau is monotonic, it is guaranteed, least fixed point is guaranteed to exist and to be unique. And this computation of the limit of a tau will terminate for some finite number of, after finite number of iterations. This thing is applicable to infinite state systems also. In case you need an additional property called continuity. And this method of computing tau as a limit of an ascending chain of tau may no longer terminate. Okay, but that's an aside. Okay, so we will revisit Kleene-Tarski theorem. Okay, later on, and so once we, as I said, look at characterization of CTL operators as fixed points. Now, as I told you, that one advantage of viewing these things in terms of fixed points is that there is a rich theory and therefore you can prove correctness. But more importantly, and also importantly, then when it is, if it is for any tau using this Kleene iteration technique, there is a common way that you can actually compute the least fixed point. That is shown by this loop in here. So you start with false, then you apply tau. You apply tau by accumulating, taking the union of tau 0, tau 1, tau 2, etc. That's what is happening here. For the specific case of reachability analysis, the tau that whose fixed point characterizes a set of all reachable states is defined as shown here, which consists of computing images for some arbitrary x and then adding it to the initial state. So is this clear? Ramalai?
Yes, yeah.
Okay, so I want to observe. So there are several fixed points. The reason that you want to insist on least fixed point is because you want to just accumulate only the reachable states and nothing more and nothing less, and that's why. So I asked this question: what are some of other possible fixed points? There can be multiple fixed points, and I told you that the set of the entire universe, true, which is represented by the predicate true, is also a fixed point. There are also other fixed points. Can you think of any other fixed point for this function tau as defined here? Yeah? Yes?
You said set of all states will be a fixed point.
That is true. The set of all states is certainly, I already told you. I'm asking you if there is something else. Some other fixed point. There are lots of fixed points. Okay, see, for example, if you start, it all depends on what you start with. In this case, you kick-started this ascending chain starting from false, which is what Klient-Tarski theorem states. To get the least fixed point. If you started with some other x, say, if the starting thing is some other x that includes I, it'll still, if you start with some x, which is a superset of I, for example, okay? Instead of false in here, you start with some x, your starting set of the chain is some x, which includes I, where it could be a superset of I, then you will get a fixed point which still includes I, but something more, okay? It also includes things, images of things that are not inside I, okay? That is also a fixed point that still includes I, okay? The true fixed point is obtained by starting this infinite chain with true, okay? Which includes all the states. So you see what the point I'm making? So you could use, if it all depends on what the starting set is of this infinite ascending chain. Okay, yeah. So then I stated that what is the symbolic formula computed after the ith iteration? What it really is happening is, if you view this as, instead of set of states, as predicates being computed, in a series of iterations, this is what is happening. So you start with false, and then each time you take the disjunction of image of that, okay? And then you add that to, take the image of false, and you add I to it, okay? And image of false is false, and therefore this is equal to I. And then you take that itself, okay, which is image of I, and then you add to I. That is I union image of I. Then you get I union image of whatever that was in the previous case. So what you end up, this is equivalent to, after some simplification, is equivalent to I union image, one-step image, two-step image, and so on. So in this, the code that is shown here actually implements the what is called cleaning iteration, okay, of the thing. It really implements the union of it's a way of computing starting from false, okay, the limit of this infinite ascending chain. So what it does is, what it returns is, for finite state systems, it is the fixed point, which is the union of all these images until you reach an n, which is the point at which you reach the fixed point, okay? And that's what this thing is, computing, okay? So is that clear? So literally what it is returning as a symbolic, as a formula, is a formula of this, denoted by this, okay? And if you expand image out, what will happen? Image itself is represented by this existential quantification. Therefore, each image I will have I nested existential quantifiers, okay? And it's a disjunction of a series of increasingly nested existentially quantified formula, okay? And that is still a propositional formula, correct? And that's what this thing computes. And what this denotes at the end, when you reach the fixed point, is the set of all reachable states. Okay, is that clear? Any questions?
Yes, sir, it's clear. And I have one question. I understand how this computes the formula for Vx. It just has to, while doing the second iteration of computing tau, it has to verify that any one of the states satisfy the property, right?
Oh, correct. So what is your question?
My question is, how can we compute G for that?
How does it?
How does it compute a path from, like, e.g.,
AG, this is not exactly directly, I mean, see, this one is not computing AG of P, okay? What it is doing is, we will see how AG of P, EG of P, etc. Can be defined, okay? This is, all I'm saying is I chose the reachability, the set of all reachable states. So what this is computing is set of all reachable states starting from a set of initial states, okay? So, yeah, in order to check if all those states satisfy P, of course, one way of doing it is if you know, you will have to check that you know, this formula you know, this implies P, okay? That's what you have to check, okay? That is one way of doing it, okay? So this one is a set of all reachable states. You have to check that every state that is included in this, that is true of this formula, that is represented by this set, is indeed satisfying P. So you have to prove, in order to show that AG of P, you know, using reachability analysis at least, you will have to show that this fixed point that you compute implies P. Okay.
Okay. Actually, I was asking about EG, but since we are computing EG, we can just map it.
You will get. So that's what I'm raising here.
Okay.
So I mean, that is true for both AG as well as thing. I mean, you can ask that question for AG of P also. I mean, and then for all CTL operators. Okay, and that's what we will do as the next thing. Okay. Okay, so this for image computation for reachable computing set of reachable states from a set of initial states, you can use this. So let's first, you know, we've already seen this. F denote the set of states satisfying, you know, so EX of F. So let's start with EX of F. I mean, EX of F and AX of F do not require really computing fixed points because they're one step relation, right? So EX of F, since we are doing it for all CTL operators, let's start with EX of X, EX of F. So assuming that you already have a characterization for F, then EX of F, that is the set of all states denoted, is denoted by this symbolic formula, correct? So this one is not the image, it's actually a pre-image. It is the set of all states that from which in one step there is a successor which ends up in a state that satisfies F. So this is a pre-image, unlike an image which was computing the set of all successors mapped from any state inside Z. What this is doing is, given an F, given a set of states that satisfy F, here you see the existential quantification is over the post state S prime. Therefore, what is free here is S. So any S that satisfies this existentially quantified formula is a state such that from that state, there is at least one successor that leads, that ends up, a successor that ends up in F, that satisfies F. Okay? So EX of F can be characterized by this one. Is it clear?
But that, yes, need not to be a initial state, right?
Oh, that may not be initial state. No.
Okay.
Yeah, you're right, because that's how EX of F semantics is defined. Okay, so this need not be an initial state. Okay, if you want to check if indeed the initial state satisfies, then you will have to ensure that you have to show that indeed I is included in that. Okay, yeah. So this is how the semantics of CTL formulas are defined anyway. Okay, it's a set of all states. Okay, that it's a set of all states that satisfy EX of F. Yeah. So I'm starting.
Okay, sir. Okay.
Yeah. So this is just a starting point. Okay, it gets interesting when you get to EG and AG, AF, and those kinds of things. Similarly, AX of F can be represented by this formula. Okay, it says that it is the set of all states such that every successor from that under T will have to satisfy F. Okay, so that's why I call this as an existential pre-image. This is a universal pre-image. Okay, so you know, for every S prime, if T, I mean, for every successor that S of S, for every S who which has a successor S prime, that has to be Fs prime. So which can also be denoted as the negation of this existential, and this is a pre-image. Okay, so the you know, your question of how do you you know, what is the tau? How could you characterize EG and AG, for example, EG as, or EF, EU, etc., as fixed points of appropriate tau, will be done in terms of EX and AX. Now, so the first thing that we will look at is what's a suitable tau for computing E that can characterize E of F until F2 as a fixed point of. Okay, so we'll start with F until F2. Okay, and we'll look at so here it comes in handy to recollect your expansion law. Remember that we had put up an expansion law. Okay, if you look at that, it gives you an idea of how you could define an appropriate tau whose fixed point can be this you know, the set of states satisfying EU. So EF until E of F until F1 until F2 is true, that if it is true of any state that satisfies F2, or it has to, I mean, F1 has to be true now in the current state, and in the next state, there must be a next state from the current state in which itself satisfies E of F1 until F2. Okay, so this was the expansion law. We didn't dwell too much on this. See, this is actually a way of recursively defining what the set of states that E F1 until F2 ought to satisfy. You see, now this gives you an idea of what the tau should be for, you know, representing, I mean, whose fixed point will represent the set of states that satisfy F1 until F2. So just replace, okay, so you define a tau. So here is the tau that I'm defining. So the Z here takes the place of E F1 until F2. So this is a recursive equation. Okay, so tau Z is defined as F2 or F1 and EX of Z. So, and then the fixed point of this will, which is what is denoted by you know, this notation, will accumulate all the states. So effectively, if you were to be using Kleene iteration, what you would do is you will start with F. You will start with F. First start with all the states that satisfy F2. And then to that, you will add in one step how you would satisfy. You remember that's how you did the explicit state model checking. Here we are just doing it over symbolic formulas. Okay, so let's look at that. So this is what I'm claiming is the EU operator can be characterized, defined as the fixed point of this tau. So what exactly is going on? To understand that indeed the fixed point indeed characterizes a set of all states that satisfy this E F1 until F2. Let's look at a bit more pictorially. Okay, so what is F2? See in this picture here, you can see the picture, right, Parmalai?
Yes, sir.
Yeah, so I'm starting with F2. So if you were to, okay, now what I'm saying is look at what is clean iteration. This is certainly a monotonic operator, isn't it? Because you are adding something, okay? This one is always, I mean, yeah, so you're adding things. So Z, when it is, if it is false, EX is false, and F1 will be false, okay? So tau 1 will be F2. Okay, tau 0 is always false. That's what clean iteration says. So you start from false. And if you apply tau to false, if you plug in false to Z, EX of false will be false. F1 and false is false. So you're adding F2. So, and that is exactly F2. See, the set of all states, I mean, this set F2 will include lots of things. It is all the states that include F2. But you see, that one is not entirely the set of states that satisfy F1 until F2, because it will also have, it certainly includes everything that satisfies F2, and also includes things like this, okay? Like, things that always satisfy F2, and there can be loops of this kind. But what it does not include are states that don't satisfy F2 of something like this. Look at the cursor, okay? So this is a state that does not satisfy F2, but satisfies F1. So here is the F1 state in here, okay? Set of all states that satisfy F1. So that in one step leads into something. It satisfies F1, but not F2, but leads to something. It has one successor which ends up in, one successor in an F2 state. And that's what you need to add, okay? And that's how you do. And the reason that this is the fixed point, you can understand it using, see if the clean iteration that when you apply to it is thing, because tau is indeed adding F2 to some Z in each step, therefore it is monotonic. And therefore, and what it is actually doing, the clean iteration, which is, as per Kleeney-Tarski theorem, is guaranteed to compute the least fixed point, is this is what is happening. Okay, when you reach the fixed point, you would have accumulated everything, okay, of these things, but not these kinds of things. See, F1 will also have things that end up never satisfying F2. Okay, this is something that does not satisfy F2 in here. Okay, so if every state, every successor state from an F1 state never leads to something F2, those things are not added. You only add those things which has at least one successor which will eventually lead to F2. And that's exactly what the fixed point of the tau that is defined here will include, and only those. Yeah?
Suppose in our model, if
you have to speak up. Yeah.
Yeah. Suppose in our model, if F1 is released before reaching F2 for every path, then
but then this will not include that, because
then tau will contain only the set of states which satisfy F2. That's it, right?
No. Oh, if there's not, if there is no F1 at all, if in your model, okay, yes, then it will only be F2, correct? Yes. So then this step, you will reach fixed point very quickly, okay? In one step itself, you will reach fixed point because there's nothing to add beyond F2. So what's happening here is all these concentric circles here are all empty, okay? I mean, they're not empty. They're all, yeah, they are empty because they all are states of this kind, like what I've shown here, okay? Here. So this is a state, for example, that I've shown here is something that is an F1, but every successor state does not. It never satisfies F2. Okay, it's outside F2. Okay. So and look at this. So that's what will happen. Okay. So yeah, maybe the case that you mentioned is an extreme case. Okay, where all these concentric circles are just empty, and then you only have this one. And there's no F1 state which will ever lead to F2. Then you will reach fixed point even quicker. Yeah. So in each step, this cleaning iteration and the symbolic model checking, what it's doing a breadth first thing. In one step, it is accumulating all the states, okay, that in one step, go to something which satisfies F2, okay? So although I've shown only one instance, that each iteration, cleaning iteration, tau 1 will include all the states that in one step end up in the fixed point. Okay, that's why this one, unlike the explicit state approach, where you kind of do accumulate one step at a time, this has a more breadth first thing, okay, which I had already shown in the reachability analysis itself. So each step in the cleaning iteration of fixed point computation is accumulating a whole number of whole bunch of states. Okay, and that's why symbolic model checking in some situations, there is a lot of connectivity. It also depends on the connectivity. Will accumulate a lot more states, and the number of iterations that you require to reach fixed point in general will be much smaller. Anyway, that's an optimization thing, okay? So for now, I want to make sure that you understand that what exactly this function, this predicate transformer tau does. And now I'm saying that it indeed is, in terms of clean iteration, what is happening is exactly shown in this picture, okay? So is it clear? Any questions?
No, sir. It's clear.
Okay.
I have.
Sure. Ask me.
So, in the formula for EF from union, in the last we have put EX of Z. So
correct.
When Z is true, that means.
No. When Z is true, what happens if you kickstart it from true? Is that your question?
No. When Z eventually gets to true, what it means is that from the current set of states,
eventually Z never gets, that is not what's happening, okay? What's happening is you're starting with Z is equal to false, okay? So tau 1 is tau of false, which is F2. Hey, it's one thing, okay? I mean, without actually, yeah. So I'm illustrating the fixed point, assuming that you believe, you trust me that Kleini's fixed point theorem is true. What's happening is the least fixed point can be computed as a limit of a series of tau chains, okay? So what are the tau chains? I mean, you can work it out. I showed you for image, okay? So what's happening here is, so tau 1 is F2. Tau 2 is all this first concentric circle here, union F2.
Yeah. Okay. Okay. Yes, sir.
Tau 2 is union of the second concentric circle, first concentric circle, and the third, and so on. Okay.
Yeah. Okay, sir. Okay.
Yeah. So eventually, when tau I plus 1 of false becomes equal to tau I of false, that's how you should be asking the question, not when z is equal to true. Okay. When tau I plus 1 of z is equal to tau I of z, false, okay, because you're starting with false. So when tau I plus 1 of, when you reach an I such that tau I plus 1 of false is equal to tau I of false, that's when you will end up accumulating all the states that satisfy E of F1 until F2. Okay? And that is the fixed point of tau, the least fixed point of tau.
Yeah. Okay, sir. Okay.
Yeah. So if you plug in true here, what will happen? I mean, what you will end up getting will be, I mean, some other fixed point, but that is not the least fixed point. Okay. So what will happen? This itself will be true, and this will be F1, F2. So if you do from true, you will not get a fixed point. Okay. So you will have to start from false. Okay. So to compute least fixed point as a limit of an ascending chain, Kleini's theorem says that you have to start from false, and that's what is happening. Yeah.
Yeah. Okay, sir.
So similarly, for characterizing a u as a fixed point, the tau that you need is very similar to this, except that at each step you will have to include. You have to do an AX. You will have to add that state to F2 only those states whose every successor leads to something which is in an F2 state. Okay, so you cannot have states like this. Here I added it to F2, any F1 state, even if it had one successor, whereas here you will have to use AX, the A pre-image, okay, to add in each step. Then you will get AF. Okay, so you can't be including these states. It is more stringent. You will have to include only those states if every successor of that goes into then you get A. I mean, one way of ensuring is you will have to draw up this Kleini chain starting from false. What happens, and then that's how you have to visualize, and that's what I've done here. Okay. Now, it seems like there is some magic going on here because of the way the thing is. Therefore, you can ask the question: how do you actually prove that the least fixed point includes exactly those states that satisfy AU? Okay. Now we will see proofs of this. Okay, I'm giving you an intuitive feeling by picturizing the Kleini chain. Okay, in order to do this, this has to be done by induction on the number of steps and the number of steps that you need to get to the Kleini iteration, as well as the number of the length of the paths from any state that you need to consider to show that it satisfies AU. Okay, in order to show that this set of states, as per the formal semantics of AU that we have defined, CTL semantics, is exactly equal to the set of states that are included in the fixed point, which is computed as a Kleini chain. It has to be done by induction, and we will see a proof later on. Okay. But my goal is for you to get an intuition, based on a simulation of the Kleini chain. Okay. So now, sometimes fixed points can also be calculated. It's convenient. They can always be also be calculated as limits of descending tau chains. If tau is monotonic, you start from true, and then you can identify define a tau such that every time you apply a tau, you are reducing the cardinality of the set. Okay, so in the fixed point that you reach, the greatest fixed point of that descending chain can also be another way of computing, and it is sometimes convenient, especially when you have EG, AG kind of things. It is convenient to visualize them as limits of the greatest fixed points of descending tau chains. Okay, so in this, the cleaning iteration works as follows. You start from true. That is the set. You start from the entire universe of states. And your tau will be defined such that every time you apply, some subset of states will be removed will be taken out of this queue. And that's why I call this as every time you apply tau, it is a descending chain, because the set that you get, the set of states that you get gets smaller and smaller as you traverse down the descending chain. And eventually, when it reaches a fixed point, it will be the greatest fixed point of such a tau, okay, which will be a least fixed point of some other tau, but it is sometimes convenient to represent your analysis, the CTL operator, as a limit of a descending chain. And while EG of F can indeed, GFP here stands for greatest fixed point, not a LTL formula. Okay, so strictly speaking, once you have AU, you have EF and AF. So EG and AG can be also expressed as negation of these things. Okay, you can, but it is sometimes useful to visualize them as this point, because as you move forward, you will see, you will get, and that's what I'm going to describe now. So we will be defining EG of F as the greatest fixed point of a descending chain of suitably defined tau. That is the greatest fixed point. Once again, to see what tau, whose greatest fixed point will be exactly those states that satisfy EGF, to understand that, we will have to recall the expansion law of EG of F. What is EG of F? It is those states that satisfy F, and every state that satisfy that F, also its next, in the next state, you will have to have there must be at least one successor state which also satisfies EG of F. Okay, that is how the expansion law, the set of all states that satisfies EG of F, is recursively defined. Okay, inductively, you can say inductively defined. So my claim is, then we define tau Z to be this one, F and EX of Z, for any predicate or subset of states Z, then the fixed point, the greatest fixed point of such a tau is the set is exactly the set of all states that satisfy EG of F. See, this tau is expressed now as F, and see, it's taking away because it is constraining more and more. Okay, given the set of states that satisfy EX of Z, it is adding an additional constraint to F. So every time you apply, starting from true, every time you apply tau, you're getting smaller and smaller states because in each step, you're taking a conjunction of whatever that you get from the previous step, and you're adding more constraints. Okay, and that's why, like this procedure says that Kleene iteration says, oh, you can compute the fixed point of this by starting from true, and then for Z, and then repeatedly applying tau to that. So let's see what happens when you simulate this on in a Kleene chain starting from true. See, when you plug true to Z, what happens? What does this reduce to? Suppose, what is tau of true? Tau of 0, tau to the power 0 is true. What is tau of true? What is EX of true, Paramalai?
Tau of, for this formula, we will get the set of all states which satisfies F.
Correct.
And the states which are next to F.
No. I asked you a very specific question. When I plug in true to Z, what is F and EX of true?
It's a set of states that satisfy F and
that's exactly what I've shown here. Okay. So in one step, tau 1 of true is F, which is what I've shown here. Okay. And note that that state, of course, every state in that satisfies F. It'll have two kinds of states. Okay. So these kinds of things where you remember how we did in the explicit model checking, explicit state model checking, you started with what was the idea for computing EG of F? You started with the strongly connected component, every state of which satisfied F. Okay?
Yeah.
Yeah. So this F, the set of all states, F includes those that are already in the fixed point, but those that should not be they will also have some states. Okay, see, for example, for these kinds of things that are either as part of a strongly connected component or that lead to a state in a strongly connected component, every state EX will end up satisfying F. Okay, but the set of all F states can also include it's an F state, but it leads in one or more step to something which may not satisfy F, okay, of this kind. Okay. So here, this is a state whose every successor, it has only one successor as shown here, will end up not leading to something which does not satisfy, which does not satisfy, which at least one of which does not satisfy F. These are the kinds of states that you will have to remove from F. You only need to retain these kinds of things. Now, if you're able to investigate the entire graph and then pick your strongly connected components, you could have started from this. But here, when you're doing it as a chain of descending chain, what you really have to visualize as each step you will be removing something which violates, which currently is in your ith step of your Kleene chain, but it has to be removed. Okay, and these things are those states whose violation can be shown in one step, two step, three step, and so on. So this is a state in one step it leads to something which leads to not of F, and so on. Okay.
Sir,
Yes.
so in that formula, what if we substitute Z with true? What will EX true will give us?
EX of true is true.
EX of true.
Every state, true includes every state. Okay. So you're saying, what are the states that in one step will satisfy true? Any state, every state satisfies true. Huh?
Okay, I get it. Yeah.
Yeah. So you're asking the question. Yes. Okay. True is any state satisfies true. So you ask the question. So what are the set of states whose at least one successor state satisfies true? I mean, any state satisfies true. So you can start from any state, and its successor state is bound to satisfy true. Yeah. You got it?
Okay.
So the claim is EG of F can be denoted as the greatest fixed point. It's the notation that's used is nu, okay, not nu of this thing, okay, and that is computed as using a descending Kleene, a conjunction of descending Kleene chain. When I say Kleene chain, what I mean is tau true starting with true, that is tau 0. True is tau 0, and tau 1 is tau of true. Tau 2 is tau of true, and so on. So tau 1 of true is what I've shown here, and I've also shown that has some things that must be included in the fixed point, but it also has things that should be removed from the fixed points which do not satisfy EG of FF, and that's what happens here. Okay, so here is the big circle. Here is F. Okay, that is tau 1. So true is this entire box. Okay, square box. So after one step, you get F. Okay, F is all the states that are included in this big circle here. And everything outside of that is not of F. So first, when you apply tau 2 of X will remove things of this kind that I've shown here in this slice, in the leftmost slice, okay? Which is a state. So you look at this state. Every successor is something that will lead to something which is does not satisfy not of F. That is EX. This is an F state, yes, but it is but EX. It does not. It's not true of EX of F. Okay, because every successor, this particular state violates EX of F, because every successor is a not F state. So after tau 2 will be that subset of F after having removed the leftmost slice. Then when you apply it, tau 3 will then remove those states which in 2 steps, okay, lead to something which violates, and so on and so on. Okay, until you have removed everything, and you would only be left with things that, those F states that have at least one path leading to something, and where every state is an F state and it ends up in something whose, which is a strongly connected component. A strongly connected component is characterized by something where every state on that cycle that is included in the strongly connected component satisfies EX of F. Okay, And that's what, that's what is happening. I mean, actually, this whole thing satisfies. So these states can have one successor that is leading out. That's okay, because that's what, that's why we're using EX, okay, since we're using EX, okay? And that's okay, because as long as there is at least one successor that leads to something inside the fixed point. So the cleaning iteration is exactly doing this, okay? Starting from true, and then a repeated application is this clear? Any questions?
No, sir.
So now you could see all the rest of the formula, AG, I mean, you can either express them as least fixed points of a suitably defined tau, or a greatest fixed point of a suitably defined, the descending chain of a suitably defined tau. The greatest fixed point, the formula usually will have to be defined as every time you apply it, you're, getting a smaller set. So it is still, such a tau is also monotonic, okay? And that plus the fact that you only have finite number of states will guarantee that in some finite number of cleaning iteration steps, you will reach your fixed point, which exactly correspond to the states denoted by the application of the CTL operator to subform. Okay. Now, so with this, you are ready to implement a CTL model checker. Okay. Because all you have to do as an exercise, this is actually given in the book also, a good exercise is for you to define a tau for AG, R. Okay, I certainly recommend that you define for R what that tau should be. I think it is given in the book, but simulate and convince yourself. Draw a picture of this kind, okay, to convince yourself that AR, how it could be defined as a greatest fixed point of a descending chain. So that will help you make it very clear, that it will ensure that you will understand this. Okay, I will include that in the written part of your assignment soon. So now, assuming that all of them can be implemented as a tau, and all the taus will only use EX and AX. Okay, so each CTL operator that requires a true fixed point, itself will be can be implemented in terms of using EX and AX. As you saw, EX and AX can be implemented using existential quantifier. So an implementation, and you saw, in the BDD lecture, how you could do existential quantification elimination over a formula, a propositional formula that is represented as a BDD. Okay, so at the bottommost level, you given a P formula. This is how the structure of your implementation of your CTL model checker, a symbolic model checker and implementation would be structured. Okay, at the bottommost level, you will have a function which just implements EX and you can do AX also if you wish. Okay, EX and AX. Okay, that itself. See, all this will be a program which will be parameterized with respect to a transition relation, but it will take some arbitrary formula representing a set of states and return a propositional formula. So this itself can be implemented in terms of, given a set of variables, you will have to existentially quantify those variables out. Okay, so you will start with gen exists. Generate an existentially quantified formula, which is available as part of your library, BDD library. Then you will implement EX and AX also as the need. Then you will have one implementation for each of the CTL operators. which will be implemented using either EX or AX, as the case may be. And it will implement the fixed point cleaning iteration loop, okay? Given the set of formulas denoted by the sub-formula inside a CTL formula who's rooted at this CTL operator. Okay, so all this is a program that maps a propositional formula denoting a set of states to the result of applying EG to that. At the topmost level, this will be you can implement them as a recursive function or a loop. Okay. At the topmost level, your model checker will take a CTL formula, which is a hierarchy of, which contains a hierarchy of CTL operators. Okay. And then given a CTL formula, it generates a propositional formula. Of course, I should have included some P formula also, because at the leaf of these will have CTL formulas. They will be represented. I mean, the atomic CTL formula will be propositional formula. Therefore, either you can say that that is included as part of it, or they are. I mean, I'm assuming here that it is embedded inside that. Okay, and this produces a Boolean result. Okay, and this generates a P formula, proposition formula, corresponding to any CTL formula which is passed as an argument, and then generates. I mean, the P formula will use these e.g. EU, gen EG, gen EU, etc., to construct the propositional formula that represents, it characterizes a set of all states that satisfies the CTL formula. Then you will check if the initial predicate that is included in the Kripke model implies that F. If that is valid, in that case, you will return true, otherwise, you will return false. Okay? This is how you will be implementing the thing. Okay. Okay. Yeah, any questions?
No, sir.
Okay. Now maybe I have, how many slides I have? Just one more slide. This is I will go through the slide, but I will go through it again, okay? Because I know that you are at the end of the thing, and then I mean, so far what I have shown you are just fixed point characterization of each CTL operator. Okay. Now, the question that I'm asking is how, I mean, can you characterize this? Can you characterize the CTL, I mean, the model checking of CTL model checking under fairness, okay, as also as fixed points, okay? That is, in other words, can I define a tau? Okay, this is what I'm asking. Can me model checking under fairness, that is, can I implement EG of F, EF of G, that is, EG under a given fairness condition? As you know, EF of G of for any formula F is not expressible as a CTL formula. But now you have a very powerful operator. I mean, which is the fixed point operator. So the question that I'm asking is, which is more powerful than the CTL operators? Yes, every CTL operator, we saw how it could be implemented or characterized in terms of the fixed point operator. So, you know, so can EF, the set of all states, satisfying EF of, you know, G of F, for example, be characterized using a fixed point? So the thing is that the answer is yes, you indeed can. Okay, and the tau formula that you need to construct is a little bit clever, and it is somewhat tricky. Okay, so I'm going to illustrate that here. I will do it quickly. Okay, and what is the time? Okay, so I have till 1:05, right? So, yeah. So I will do it quickly, and I will go through this again. I want to finish it off so that this will be recorded, and you can go through it, and I will re-explain this since the others are missing as well. Now consider a fair, as an illustration, consider a fair Kripke model with the fairness constraint F defined as in terms of two predicates, okay, P1 and P2. So which means that you have to restrict your model checking to all those paths, infinite paths, in which the states that satisfy, in which P1 and P2 occur, each of them occur infinitely often. Okay, you remember that, correct, Paramalai?
Yes, sir.
Okay. Now the question that I'm raising is, using, say, existing CTL operators, for which we have defined, we know how to implement, and using a fixed point operator, suppose it is at our disposal, can I define, can I characterize this, okay, as a fixed point of a tau. So we'll start with, consider this formula. Okay, this one. What does this formula denote? So just look at the top portion. So here is a picture of the set of states that satisfy this CTL formula. See, by the way, how did you, Paramalai, how was this model checking under fairness implemented in explicit state? Do you remember?
I don't remember that.
Yeah.
But we saw that in last class, we saw that.
That's correct. So I remember, so I will refresh your memory. So you started with a fair, strongly connected component, e.g. in explicit state model checking, much like in the symbolic model checking that we just now saw, where it computed, you started, for, e.g. of F, you eliminated, you removed all the states which had not of F as labels. You only kept F. Okay, that's what the greatest fixed point clean iteration did just now as well. Okay, now from that, but in that you retained, once you removed all those things, normally you would have kept all kinds of strongly connected component inside that, inside your graph, but you restricted yourself to those strongly connected components that were fair. That is, those strongly connected components on which P1 and P2, each of them held infinitely often. Okay, so this is not exactly what the thing is. See, what F and this formula, EX of EF until P1, just look at the picture above. What it does is, of course, that every state of that satisfies F, and every state of that is such that in the next state satisfies EF until P1, as well as EF until P2. So for example, this one is an F state. This circle here includes only F states. So this satisfies F, the starting state of this path. Then it also satisfies EX of F until P1 as well as F until P2, because F is satisfied here, and the next state P1 and P2 satisfies, and there is a loop. Okay, that's a strongly connected component in which P1 and both P1 and P2 satisfy. Similarly, it is the case here. Of course, it will have all these kinds of things, but it will also have things like this. Okay, so this state that is only strongly, see, this strongly connected component in here is a fair strongly connected component, but this one is not a fair strongly connected component. Why? Because it has, I'm sorry, this one is as well. Okay, I should not have had this back loop. Okay, sorry about that. Okay, both these show strongly connected. So for example, if you did not have this thing, show here. So here's what it is. So this one state here is something in which P1 holds, but it is not. It is part of not a strongly connected, fair strongly connected component. So you need to remove those kinds of things. Okay, this already includes fair strongly connected states which are on fairly F states which are on fairly strongly connected components. One in which both P1 and P2 happen infinitely often. But unfortunately, it also includes those F states which in one or more steps lead to some strongly connected component which is not fair. Okay, and that is what you need to get rid of. Okay, so starting with this, okay, so you could, this kind of E that you had in here, you can use that as a starting point. Okay, and to get your tau to do it. So the tau Z the tau should be such that every state in that given as Z should be an F state, and every state on that is such that in the next state F until Z until P1 holds good. Okay, and if you see that and the fixed point of this would be such that it would have removed all the states that satisfy that violate these states that are leading to unfair strongly connected components, and keeps only those which lead to some fair strongly connected components. Therefore, EF of G of F can be defined as the greatest fixed point of a tau, where tau itself is expressed in this this fashion as a conjunction of these two things. So in general, if you had if your fairness constraint had n fairness predicates, your EFGF can be expressed as a greatest fixed point of a tau, which is defined like this here, okay, as shown here. You'll have one EX EU for every fairness constraints, okay, corresponding to every fairness constraint. And so that when you do clean iteration on that, you will see you will in each step remove those states. In tau 2, you will remove those states which lead to a unfair strongly connected component one step, and then tau 3 will remove those states to lead to unfair strongly connected component 2 steps, and so on and so forth, so that eventually you'll only keep those those things that lead to are fair strongly connected components. Okay, so we will look at that, and I think you need to think about this review, and then we will I will go through this again in the next class. Okay, so so I'm not sure if you were able to grasp this aspect completely, Paramaline, But if you do have any questions, please let me know. But I will go through this again in the next class as well for the benefit of the other two people. But do you have any questions?
No, sir. I'll also read through this in the.
Okay, fine. Thank you. Then I will stop share. I will